in the deep night of prehistory, when firelight was new and language was still gathering itself. There were no written records. The sky above was a dark canopy pierced by points of light, and those lights were woven into stories whispered by elders around embers. People sleeping under the open sky thought of the stars as their ancestors, as campfires of unseen beings, or as holes in a vast black tent through which a greater light beyond might shine. In the myth cycles of Australian Aboriginal cultures, there is an image known as the emu in the sky. It is not drawn from dots of light, but from the dark gaps between them. The body of the emu is shaped by the dark dust lanes of the Milky Way, and the bright stars around it only outline a void. This way of seeing tells us that from the very start, human beings looked up and found meaning, not only in what was visible, but also in what was hidden. On those ancient nights, the slow turning of the heavens would be felt more than seen. The apparent motion of the stars around the pole was the longest clock any observer could imagine. Sitting by a campfire, watching sparks rise and fade into the dark, one could feel the earth turning beneath them. It seemed as if the sky stayed pinned in place, while the ground subtly shifted. The rotation was so silent and so patient that it took generations to grasp. That sense of turning without end gave the first watchers a rhythm to life that had nothing to do with the rising and setting of the sun. It was a rhythm that eased minds into sleep, even as curiosity pulled their thoughts toward the patterns above. The sensory world of those early nights was intense in its simplicity. Sparks leapt from the burning wood and curled upward, glowing orange before vanishing into the black. In the distance, the silhouette of a tree might blur into the dome of the Milky Way. The soft crackle of the fire mingled with the quiet breath of the earth itself. Around the flames, stories passed from mouth to ear. Each tale fixed some bright point in the sky as the eye of a god or the tail of a beast. The firmament became a canvas for the imagination, and yet it was also a source of very real comfort. To look up and see the same stars night after night was to feel anchored in an environment that could be harsh and unpredictable. Even without writing, people noticed regularities. They knew that certain patterns would return with the seasons, that the bright band of the Milky Way shifted its angle with the year, that the dark shapes within it marked the time for hunting or for gathering. The emu in the sky would tilt to a specific position that coincided with the laying of emu eggs, guiding families to a source of protein. Such practical knowledge blended seamlessly with myth. There was no need to separate the sacred from the scientific. Both were part of the same experience of living under the stars. As generations passed and societies grew, curiosity about the lights above did not fade. Instead, the urge to bring order to the celestial patterns intensified. Watching alone by a fire could be satisfying, but sharing observations, recalling them, and making sense of them required a more permanent record. The slow turn of the sky invited the idea that cycles could be tracked and predicted. Out of this longing for regularity emerged the earliest attempts to write down the positions of the stars and to organize them into a system. The banks of the Tigris and Euphrates were fertile not only with crops, but with questions. In Mesopotamia, around 1800 years before the Common Era, Babylonian scholars began to move beyond oral tradition. They looked up at the confusion of lights and asked how to make sense of them in a way that could be shared and preserved. The result was the Mullapin, a series of clay tablets on which priests recorded the rising and setting of stars and the movements of planets. These were not just random notes. They were attempts to impose order on the heavens, to transform the night into a map. Sitting at low tables by flickering oil lamps, scribes used a reed stylus to press wedge-shaped marks into wet clay. Each soft impression was a promise that memory could last longer than a lifetime. They logged the positions of constellations, marked the paths of wandering points of light that we know as planets, and created a scheme that divided the sky into segments. This organization gave rise to the zodiac, a belt of constellations against which the sun, moon, and planets appeared to move. By assigning names and symbols to these segments, the Babylonians could predict the return of certain stars and anticipate the positions of planets with remarkable accuracy. The act of recording brought with it a deeper appreciation of periodicity. To know that a star would rise on the same day each year, and to have that knowledge confirmed by numbers on clay, was a profound comfort. It meant that the universe was not arbitrary. It followed cycles that could be understood. That predictability had practical uses in agriculture, in ritual, and in governance. Kings consulted astronomer priests before important decisions, believing that the heavens reflected the will of the gods. The ability to anticipate eclipses or the appearance of Venus gave authority to those who mastered the code. The physicality of the tablets themselves holds a sensory memory. Imagine the sound of a stylus scratching into soft clay, the scent of damp earth in a room crowded with scholars. Once inscribed, the tablets were baked in ovens and hardened into something that could endure. Hands that had been stained by clay could hold a record of the sky that future hands would read centuries later. In this way, the stars became part of a human archive. The sky's slow patterns were mirrored in the shelves of libraries. The Babylonians did more than count and name. They recognized that some lights wandered among the fixed stars. These wanderers, the planets, did not adhere to simple cycles like the stars did. Tracking them required new forms of calculation. The interplay of regularity and irregularity sharpened mathematical skills. It also sparked a sense of wonder at why some celestial bodies obeyed predictable rhythms, while others seemed to follow their own paths. The tension between order and anomaly was fertile ground for thought. As the clay tablets accumulated and the tradition of recording continued, a shift took place. The sky was no longer a purely mythic space. It was a domain of measurement. observers began to see patterns that spanned decades. They understood that knowledge could outlast them if it was written. With the comfort of periodicity came the urge to apply celestial cycles to earthly problems. The calendar became more precise, and civic life began to align with cosmic rhythms. In this environment, another civilization looked beyond the horizon of timekeeping to use a specific star as a herald of seasonal change. The stage turns toward the floodplain of the Nile, where a single bright star would govern the agricultural heartbeat of a nation. Along the length of the Nile, life depended on water arriving at the right time. The river's annual flood turned desert into farmland, and predicting that flood was a matter of survival. Egyptian priests watched the sky with an intensity born of necessity. They noticed that after a period of absence, a bright star would appear just before sunrise. Low on the eastern horizon, the star we call Sirius, which they named Sopdet, vanished from sight for about 70 days each year because it traveled near the sun during the daytime. Its return to the dawn signaled that the inundation was imminent. This moment, when a star becomes visible just ahead of the rising sun, is called the heliacal rising. It is delicate and brief, a flash of starlight that holds only until the growing light of morning washes it away. For the Egyptians, the heliacal rising of Sirius became the anchor of their calendar. They divided the year into months based on the cycles of the moon, but they aligned their civil year to the appearance of Sopdet. Because the flood did not come on exactly the same day every year, the sight of Sirius gave early warning. Farmers could prepare the fields and ready themselves for the changing waters. The concept of a star being invisible while still present fascinated those observers. They understood that Sopdet did not cease to exist when it disappeared from the night sky. It traveled across the daytime sky, hidden by the sun's glare. The notion that something could be there, unseen but predictable, shaped Egyptian thinking. It was not just practical, it was spiritual. They associated Sirius with the goddess Isis, and its rising was part of a larger mythic cycle involving death and rebirth. The 70-day absence of the star mirrored the mummification period of Osiris. When the star returned, it was as if the god was reborn, and so was the land. Standing on the banks of the river, one could feel the humidity thickening as summer advanced. Nights were clear, and the stars glittered with sharpness. Watching for Sopdet required patience and precision. The observers had to know exactly where on the horizon to look, and they had to be awake in the dark hours before dawn. They probably felt the coolness of the desert giving way to the first warmth of morning. When the star finally flickered into view, there would have been a quiet sense of relief mixed with reverence. They recorded the moment on walls and papyrus, entwining it with hieroglyphs of seasons and deities. The heliacal rising also deepened an understanding of how the sky and the calendar could be used together. The Egyptians developed a year of 3 seasons, each linked to the river: inundation, emergence, and harvest. They created a civil calendar of 360 days, plus 5 extra days for the birthdays of gods. Every 4 years, they noticed the drift between the civil year and the solar year, though they did not correct it in the way that later societies would with leap years. They recognized the tension between different measures of time. This awareness of multiple cycles coexisting set a foundation for more sophisticated astronomical thought. As knowledge of the stars grew along the Nile, Egyptian culture blossomed with art and architecture that aligned with celestial events. Temples were oriented to capture the first light of specific stars. Pyramids were aligned to the cardinal directions with uncanny precision. The interplay of stone, light, and belief made the night sky a partner in human endeavors. Yet, for all this ingenuity, the conceptual model of the cosmos remained geocentric. The stars were believed to be lights carried by boats or born by gods. Their motions were the workings of a divine order rather than natural forces. It would be the Greeks who would craft an elaborate geometric system to explain those motions. As the Egyptian system anchored time with the heliacal rising of a single star, Greek philosophers would soon imagine that stars were affixed to crystalline shells, turning in perfect circles around an immovable earth. In the city-states of Greece, philosophy was not confined to ethics and politics. It extended to the heavens. Around the 4th century before the Common Era, thinkers like Eudoxus and Aristotle built upon earlier ideas to create a model of the cosmos that aimed to reconcile observation with a desire for perfection. They imagined that the stars were embedded in a series of transparent spheres nested within each other, all centered on the Earth. Each sphere rotated at its own steady rate, carrying the sun, moon, and planets along paths that traced circles in the sky. This concept of crystal spheres solved a puzzle. The Babylonians had noted irregular motions, but the Greeks sought harmony. Circular motion was considered perfect because it had no beginning or end and could continue forever without change. In the model of Eudoxus, multiple spheres combined to reproduce the complex paths of the planets. Aristotle refined the system by asserting that beyond the sphere of the fixed stars, there was a prime mover that imparted motion to everything else. The stars themselves were unchanging, pure, and divine. The cosmos was finite, with Earth at its center, encased in clear shells that rotated smoothly. The idea carried with it a sense of calm. If the universe was composed of crystalline shells rotating around us, then everything had its place and moved with precise regularity. There was no need for the stars to vary or decay. They were eternal, and their motion was eternal. This belief fostered a feeling of security. Just as a well-made machine runs without friction, the spheres were thought to spin noiselessly in a frictionless medium. There was even a notion of the music of the spheres, a harmony produced by the motion of the heavens that was too constant and too ancient for human ears to perceive. It was said that we could not hear it because it had been playing since before we were born. Observing the night sky in ancient Greece involved measuring angles and using simple devices like the astrolabe to mark the positions of stars. Thinkers paid attention to eclipses, to the phases of the moon, and to the wandering of the planets. They believed that by adjusting the number and speed of spheres, they could match observation. The model was geometric, grounded in the belief that mathematics reflected the underlying order of the universe. It also allowed philosophers to debate the nature of change and perfection. If the heavens were perfect, then change must be an illusion or confined to the imperfect earthly realm. Yet, even within this elegant model, there were unsettling hints of imperfection. Comets appeared and faded, bright guest stars flickered into being, and the planets sometimes reversed their course in the sky. To preserve circular motion, Aristotle explained retrograde motion by adding epicycles, small circles that rode upon larger ones. This added complexity signaled that the theory, though beautiful, was strained. Still, the image of nested spheres persisted for centuries, influencing medieval thinkers and shaping art and poetry. The sensory imagination of crystal spheres touches our mind even now. Picture transparent shells turning inside one another, sliding with no friction, their combined motions creating the intricate dance we see when we look up. Imagine, too, the low hum of cosmic harmony, not as a sound heard by ears, but as a metaphor for the underlying order. In this picture, there is no chaos, only concentric layers moving with steady grace. But beyond the Mediterranean, across a vast ocean, another tradition was taking shape. There, navigators would not be content with static spheres. They would use the stars as pointers across a restless sea. The Greek vision of fixed perfection would give way to a more dynamic, experiential relationship with the heavens. Vast stretches of water separate the islands of the Pacific. For Polynesian navigators, these waters were not barriers, but pathways. Around the 10th century of the Common Era, seafarers from places like Samoa and the Marquesas embarked on voyages that spanned hundreds of miles without the aid of compasses or maps. They relied on the stars as both guides and companions. The night sky was memorized as a star compass. Navigators learned the rising and setting points of hundreds of stars and used them to steer their canoes toward distant islands. This star compass was organized around the concept of zenith stars. Each island has stars that pass directly overhead, one for each direction of the compass. When a navigator set out from one island, he would steer by keeping the zenith star of his destination on a specific bearing. The idea that a star could connect a point of light to a point of land was both poetic and precise. It created a vertical thread linking the heavens and the earth, a line of orientation that was felt rather than seen during the day, and confirmed by observation at night. The training of a navigator involved years of learning. Boys accompanied elders on shorter trips, listening and watching. They learned to read the horizon, to note how the ocean's swell moved, and to feel subtle shifts in wind. The rhythm of the ocean swell, known as tilapa, was felt through the hull of the canoe. It resonated with the slow arc of the Southern Cross and other constellations. Sensory perception was sharpened. The smell of distant land, the flight patterns of birds, and the color of the water all provided clues. The stars provided orientation when the sea offered no landmarks. On a clear night, the sky over the Pacific is a dome of incredible clarity. The air is often free of dust, and the stars seem close enough to touch. The Milky Way stretches across the entire sky, a silver river that mirrored the ocean below. Navigators lay on their backs during rest periods, tracing the paths of stars with their fingertips and committing them to memory. The entire crew was attuned to the environment. They knew, for instance, that the rising of a particular star signaled the approach of an island long before land was visible. This intimate knowledge turned the ocean into a navigable landscape. The cognitive map of a Polynesian navigator was not static. It was a living model that adjusted to wind and wave. Navigators could hold in their mind the positions of multiple islands and the stars associated with them. They could compensate for currents, for drift, and for weather. This dynamic use of the sky stands in contrast to the Greek idea of a fixed celestial sphere. For these sailors, the stars were not anchored to crystal shells. They were waypoints in an ever-changing environment. As they traveled, navigators carried with them stories and songs that encoded star positions and directions. These songs were a form of oral cartography. They could be sung to apprentice navigators, ensuring that knowledge persisted across generations. The art was not only about reaching a destination, it was about maintaining a relationship with the ocean and sky. When a navigator saw the zenith star of a distant island climbing toward the vertical, he felt a sense of alignment, as if the entire cosmos was threading him toward his goal. The Polynesian tradition demonstrates a profound trust in human perception and memory. It also shows that precision can be achieved through experience without instruments. The closeness between navigator and sky made the stars into companions rather than remote objects. Yet, in another part of the world, a record of an unexpected light in the heavens would challenge the idea that the sky was unchanging. Observers would note a new star that was bright enough to be seen in daylight, forcing a reconsideration of cosmic permanence. In the summer of 1054 of the Common Era, sky watchers in China saw a light that had never been recorded before. It appeared near the constellation we call Taurus, and was bright enough to be seen even in the daytime for weeks. Court astronomers in the Song dynasty referred to it as a guest star because it was a visitor to the familiar patterns of the night. They meticulously recorded its position, its brightness, and its gradual fading. Their entries noted that it was first seen on the morning of July 4th, and that it could be seen for 23 days in full sunlight. After nearly 2 years, it could no longer be observed without aid. The fact that the heavens, thought to be immutable, could produce a new star was deeply significant. Chinese astronomers had a long tradition of careful observation and record keeping. They maintained star catalogs, named constellations, and monitored comets and novae. The appearance of a guest star was not merely a curiosity. It had potential implications for the emperor and the state. In the cosmology of the time, unusual celestial events were read as omens. The calm discipline with which the imperial scribes approached their work reflects both reverence and a desire for accuracy. They ground ink, brushed characters onto silk, and described what they saw without speculation or panic. From our modern perspective, we understand that the guest star of 1054 was a supernova, the explosive death of a massive star. The light from that event traveled across space for nearly 6,000 years before reaching Earth. Each photon carried information about the physical processes inside the dying star. The arrival of that light is a kind of message across time. The concept of luminosity, of light traveling vast distances and still retaining enough energy to be seen in daylight, stretches the mind. That the light left its source before many ancient civilizations had formed and reached us in the middle of the 11th century invites contemplation of cosmic timescales. In addition to the bright light, there were other signals that we now know accompany a supernova. Neutrinos, nearly massless particles, would have flooded the solar system unnoticed. They pass through matter almost unimpeded, carrying away energy from the explosion. Invisible to the eye and undetectable with the technology of the time, they are part of the quiet physics of such events. The Chinese observers could only record what they saw, a new point of light where none had been before, brighter than any star, and then gradually dimming. The diligence of the Song astronomers laid a foundation for future scientists. Centuries later, when astronomers identified the Crab Nebula, a cloud of gas and dust in Taurus, they looked back at the Chinese records and connected the nebula to the guest star. Historical records became a vital part of astrophysical research. The combination of careful human observation and the physical remnants of cosmic events allows us to piece together stories that span millennia. The Chinese tradition of astronomical monitoring contrasts with the European belief in immutable heavens that persisted well into the Renaissance. In Europe, the idea that stars could appear and disappear was troubling because it contradicted the Aristotelian doctrine of perfection. In China, the pragmatism of record keeping allowed for anomalies to be noted and incorporated. This difference would have implications when new instruments began to reveal more detail about the cosmos. The next significant shift would come with the invention of a device that allowed the eye to resolve a blurred cloud into countless individual points, shattering the illusion of a smooth, continuous Milky Way and ushering in a crowded universe. in the early years of the 17th century, a device originally fashioned for commerce and warfare was turned toward the heavens. When Galileo Galilei lifted a simple spyglass to the sky in 1609 and 1610, he opened a new era of observation. The instrument was essentially a glass eye, a tube with lenses at each end that magnified distant objects. Galileo heard of Dutch spectacles makers who had built such devices and quickly constructed his own, improving its magnification. When he pointed it at the moon, he saw mountains and valleys. When he pointed it at Jupiter, he saw moons in orbit. And when he aimed it at the Milky Way, a mist turned into an expanse of individual stars. The experience of looking through that early telescope was transformative. The Milky Way had always appeared as a pale band across the night, a cloudy pathway. Through the telescope, it dissolved into millions of tiny points of light. The universe suddenly became much more crowded and complex. This phenomenon is known as resolution. The optical system took a blurry patch and sharpened it into discrete points. Focusing required patience. The lens had to be adjusted until the fuzziness vanished, leaving crisp, hard lights. The act of focusing was almost meditative. A gentle turning of screws, a careful adjustment, and the moment when clarity arrived. The telescope also showed that planets were not perfect spheres. The surface of the moon was rough. Venus displayed phases like the moon, proving it orbited the sun. Jupiter had companions, little stars that moved around it, challenging the idea that all celestial bodies orbited Earth. These observations undermined the crystal sphere model and supported the heliocentric ideas of Copernicus. Galileo published his findings in a small book called Sidereus Nuncius, or the Starry Messenger, and the reaction was swift. Some were fascinated, others were threatened. In addition to the new points of light, the telescope produced optical artifacts that became part of our visual vocabulary. One of these is the diffraction spike, a cross-shaped pattern of light that appears around bright stars when viewed through a lens, or around the secondary mirror supports in a reflecting telescope. The spikes are not real structures in the star, but results of the wave nature of light interacting with the instrument. They add a subtle beauty to photographs of stars and remind us that our tools influence what we see. Galileo's glass eye turned a theoretical debate into an empirical one. He could show, not just argue, that Jupiter's moons revolved around Jupiter. He invited skeptics to look through the telescope themselves. Some refused, fearing that the instrument might deceive them. Others looked and could not deny what they saw. The telescope became a bridge between mathematical models and physical observation. It also democratized the sky to an extent. A person with a modest instrument could see things that no emperor or philosopher of the past had seen. The sense of wonder that accompanied these discoveries cannot be overstated. To see the universe populate itself with countless new stars was to feel both small and exhilarated. It changed the way people thought about Earth's place in the cosmos. It raised questions about the nature of stars and the forces that moved them. Those questions would lead to investigations into motion and gravity as more accurate instruments were built and more precise measurements taken. People realized that stars themselves moved through space. The next step in our story involves a connection between motion on Earth and motion in the heavens, bringing a new understanding of inertia and gravity. In the latter half of the 17th century, the idea that the stars were fixed points on a sphere was challenged by evidence that they had their own motion. English astronomer Edmund Halley compared ancient records with his own measurements and discovered that stars like Arcturus and Sirius had shifted positions relative to the background. These shifts were small but measurable. He termed this movement proper motion. If stars moved, then the crystal spheres could not exist. There had to be another explanation for how celestial bodies behaved. Isaac Newton provided that explanation in 1687 with the publication of his work on the mathematical principles of natural philosophy. He formulated the law of universal gravitation, stating that every mass attracts every other mass with a force proportional to their masses and inversely proportional to the square of the distance between them. Gravity, therefore, governed not only apples falling from trees, but also the motion of the moon around the Earth and the planets around the sun. It extended to the stars. The heavens were not a separate realm. They followed the same laws as objects on Earth. One of Newton's insights was the concept of inertia, that an object in motion stays in motion unless acted upon by a force. If stars were drifting, it was because they had been set in motion long ago and nothing had stopped them. They did not need a crystal sphere to carry them. They floated in a void, moving through space with velocities that could carry them across the firmament over long spans of time. Halley's observations fit neatly into this framework. Proper motion was a consequence of stars being massive bodies with their own trajectories. The idea of gravity gave rise to the concept of a barycenter, a common center of mass around which two objects orbit. When two stars form a pair, they do not revolve around one or the other, but around a point between them determined by their masses. This is like two dancers spinning while holding hands. Their individual motions trace circles around a spot in empty space. The barycenter may lie within one of the stars if there is a large difference in mass, or it may lie in the empty space between them if the masses are comparable. The notion that invisible points in space could serve as centers of motion was radical and elegant. These insights shifted the universe from a system of rigid spheres to a dynamic interplay of bodies. Space became an arena in which masses attracted each other and responded according to simple rules. The mathematics of these interactions could predict orbits and trajectories. It also meant that the cosmos was not static. Stars could wander, pairs could dance around barycenters, and clusters could drift apart. The night sky became not a fixed tapestry, but a constantly evolving scene. The sensory image of inertia in the void is one of serene, unstoppable motion. Imagine a giant sun drifting through darkness. No engine propelling it, no friction to slow it, just its own momentum carrying it. Beside it, a smaller companion star keeps pace, both revolving around a point in space that is empty. The two are bound by gravity, yet separated by distance. Their silent dance continues for millions or billions of years. This picture contrasts with earlier models that needed physical structures to explain motion. It also sets the stage for efforts to measure how far away stars really are and how fast they move. As astronomers grew more precise in their observations, they began to wonder about the distances to those moving stars. They knew that if stars had proper motion, they must also have parallax, a slight shift in position when viewed from different points in Earth's orbit. Measuring that shift would reveal their distance. This task would require even more accurate instruments and immense patience. The next segment of our narrative turns to the first successful measurement of stellar distance and the sobering realization of the vast emptiness between stars. In the early 19th century, Friedrich Bessel undertook a measurement that would redefine our sense of scale. Using a precise instrument called a heliometer, he measured the tiny displacement of the star 61 Cygni relative to more distant stars as the Earth moved from one side of its orbit to the other. This displacement is known as parallax. When you hold up a finger and alternately close each eye, your finger appears to shift against the background. The closer your finger is, the larger the shift. Applying this simple geometry to the stars, Bessel calculated that the distance to 61 Cygni was such that the parallax angle was less than 1 second of arc. This is like measuring the thickness of a human hair held at a distance of 20 miles. The result was astonishing. The distance turned out to be over 10 light years, meaning that light takes more than 10 years to travel from that star to Earth. Since light moves at about 186,000 miles each second, the physical separation is trillions of miles. The universe was larger than anyone had dared to imagine. The space between stars was not filled with transparent spheres. It was mostly empty. The realization of this vastness had a profound emotional impact. It stripped away comforting notions of a cozy cosmos and replaced them with a sense of isolation that was paradoxically soothing. Isolation means there is room for motion, time for journeys, and a silence that is not threatening but profound. To measure such small angles required new technology and careful technique. Bessel observed the same star repeatedly over months, accounting for atmospheric distortion and instrumental error. His success showed that with patience and precision, humans could measure distances far beyond Earth. It opened the door to mapping the positions of stars in 3 dimensions. The method of parallax remains foundational in astronomy today, extended by space-based observatories that avoid atmospheric interference. The concept of parallax connects to everyday experience. When you move your head from side to side, nearby objects shift relative to distant ones. That is parallax. Bessel extended this familiarity to the realm of the stars. The geometric triangulation he performed is simple in principle, but difficult in practice when the angles are so small. His achievement demonstrates how the combination of a clear idea and meticulous execution can yield insights into the very structure of the universe. The emptiness revealed by parallax invites contemplation. Imagine standing under a clear night sky, perhaps on a winter evening when the air is crisp. You see countless stars, and yet between each one there are unimaginable distances. Light from each star travels through that void, crossing space for years, decades, centuries, before reaching your eyes. There is a silence in those gaps that feels safe rather than lonely. It is a silence that allows stars to form, live, and die without constant interference. The vastness gives room for galaxies to drift, for planets to orbit, for life to emerge. As astronomers grasped the scale of the universe, they sought to understand more about the nature of starlight itself. If stars were so far away, then everything we could know about them had to be gleaned from the light they sent us. This led to the study of spectra, the decomposition of light into its constituent colors, and the discovery that dark lines within the spectrum held the keys to stellar composition. A German optician and physicist would find these lines and unknowingly open a new field that would allow us to read the chemistry of stars without ever touching them. In 1814, Joseph von Fraunhofer, a Bavarian optician, was making precise glass lenses for telescopes. To test the quality of his prisms, he passed sunlight through them and observed the resulting spectrum. He expected a continuous band of colors. Instead, he noticed dark lines interrupting the rainbow. There were hundreds of these narrow, black lines, each at a specific wavelength. Fraunhofer carefully mapped their positions and labeled the strongest among them with letters. These dark lines, now called Fraunhofer lines, were later understood to arise because atoms in the Suna-Euro-Strade S atmosphere absorbed specific wavelengths of light. The discovery of absorption lines opened the way for spectroscopy, the study of how matter interacts with light. When white light passes through a gas, the atoms and molecules in the gas can absorb photons of certain energies. Electrons in the atoms jump to higher energy levels by taking in light of specific wavelengths, leaving dark gaps in the spectrum. Each element has a unique set of lines, a fingerprint. By examining the absorption lines in the spectrum of a star, scientists can determine which elements are present in its atmosphere. Fraunhofer himself did not know the physical explanation for the lines he observed, but he recognized their potential as a tool. He used the lines to measure the refractive indices of materials with extraordinary precision. Later, scientists like Kirchhoff and Bunsen linked the lines chemical composition, ushering in a new era of astrophysics. For the first time, people could know what stars were made of without traveling to them. The spectrum became a barcode, a coded message that could be read with a prism or a diffraction grating. The visual of a prism splitting light remains iconic. A beam of white sunlight enters a triangular piece of glass and fans out into a soft ribbon of colors. Red at one end, then orange, yellow, green, blue, indigo, and violet. The colors blend smoothly, yet the dark lines where certain colors are missing are sharp. In a laboratory, the spectrum might be projected onto a screen, with the narrow absorption lines marked and measured. Observers would stand in dim light, adjusting equipment, recording measurements. The atmosphere is quiet, focused, and filled with the faint smell of warm machinery. Spectroscopy taught us that stars are not just points of light. They are physical objects with distinct compositions. It showed that the same elements found on Earth existed in the stars. It also revealed differences. For instance, the sun contains elements like iron and calcium, but in different proportions than our planet. The method allowed astronomers to classify stars, to study their temperatures, and to infer their ages. The rainbow became more than a beautiful phenomenon. It became a diagnostic tool. As astronomers applied spectroscopy to thousands of stars, they needed a system to organize the wealth of data. Temperature, color, and spectral lines offered categories. At the Harvard College Observatory, a group of women known as computers undertook the monumental task of sorting and classifying stars based on their spectra. They would create a sequence that remains in use today, placing order on seeming chaos. This act of classification, at once meticulous and creative, would provide a framework for understanding stellar evolution. At the turn of the 20th century, the Harvard College Observatory housed hundreds of thousands of glass photographic plates. Each plate contained images of small sections of the sky. When the plates were examined through magnifying loops, tiny gray smudges represented stars. Each star's light had passed through a prism before reaching the plate, producing a small spectrum. It was the job of a group of women known as the Harvard Computers to examine these spectra and classify the stars based on the patterns of dark and bright lines. Annie Jump Cannon, one of the leading members of this group, developed a system that organized stars by temperature. She arranged spectral classes in the sequence O, B, A, F, G, K, and M, remembered by students with mnemonics. In this sequence, O-type stars are the hottest and bluest, while M-type stars are cooler and redder. The classification was not arbitrary. It reflected physical differences in stellar atmospheres. Cannon's keen eye and memory allowed her to classify hundreds of stars per hour. Her colleagues, including Williamina Fleming and Antonia Maury, made other contributions, such as distinguishing between spectral subclasses and identifying unusual stars. The process of classification was both methodical and soothing. In a quiet room, a computer would place a plate under a magnifying viewer. She would slide a loop over the glass, lean in, and focus on a tiny spectrum. The sound of the loop moving over glass would be soft and rhythmic. With a pencil, she would make notes and assign a class. The act of taking a messy pile of data and sorting it into categories has a calming effect. It gives a sense of control over chaos, a feeling that understanding is possible even when confronted with immense complexity. Beyond the immediate satisfaction of order, the classification system allowed astronomers to see patterns. When plotted in diagrams, the classes revealed a relationship between a star's temperature and its luminosity. This became the Hertzsprung-Russell diagram, a tool that organizes stars by brightness and color. Most stars fall along a diagonal band called the main sequence, where stars spend the majority of their lives burning hydrogen into helium. Outliers above and below the main sequence represent giants and dwarfs at different stages of evolution. The Harvard computers worked largely behind the scenes, but their contributions were foundational. They transformed spectroscopy from a collection of individual observations into a systematic science. They showed that the cosmos could be sorted and understood through careful attention to detail. Their work also demonstrated that the universe was not random. Stars followed patterns that could be traced and categorized. As the classes were refined and the diagram developed, another insight emerged. Spectral lines indicated not only temperature, but also composition. When Cecilia Payne, working at Harvard in the 1920s, examined the spectra with theoretical insight, she realized that stars were not composed of rock or earth-like material. They were made mainly of hydrogen and helium. This revelation simplified the cosmos in an unexpected way. Instead of being built from varied stuff like mountains and oceans, stars were predominantly composed of the lightest elements. The simplicity of this composition would become a touchstone for understanding how stars shine and evolve. In 1925, a graduate student at Radcliffe College named Cecilia Payne published a dissertation that would forever change our understanding of stars. Building on the work of the Harvard computers and applying the new principles of quantum mechanics, Payne analyzed the strengths of spectral lines in stellar spectra. She considered the effects of temperature on the ionization of atoms and realized that the dark lines in the spectra did not directly indicate the abundance of elements, but depended strongly on temperature and pressure. Her conclusion was startling. The sun and stars were composed almost entirely of hydrogen and helium. Elements like iron, silicon, and carbon, though prominent in Earth's crust, were present in stars only in trace amounts. This meant that the universe was much simpler than previously thought. At the atomic level, stars were mostly hydrogen, the simplest element with one proton and one electron, and helium, with two protons and two electrons. The energy that powered starlight came from the interactions of these light nuclei deep in the cores. Payne's work challenged the prevailing view that stars were made of material similar to Earth. Some senior astronomers initially resisted her conclusion, suggesting she had misinterpreted the data. However, later studies confirmed her results. Cecilia Payne-Gaposchkin went on to have a distinguished career, and her insight laid the groundwork for the theory of stellar structure and evolution. The concept of simplicity at the heart of stars is profound. Imagine a massive sphere of gas, tens of millions of times the size of Earth, composed mostly of hydrogen. In the core, extreme temperature and pressure strip electrons from protons, creating a plasma. Photons generated by nuclear reactions in the core take thousands or even millions of years to reach the surface because they are constantly absorbed and re-emitted by the dense gas. When they finally emerge, they travel across space to our eyes in a fraction of a second. The simplicity of composition belies the complexity of processes inside. The atmosphere of a star is not like the air we breathe. It is a thick, hot layer of gas where light interacts with atoms in myriad ways. The outer layers of a star churn with convection, hot material rising and cooler material sinking, creating granules on the surface. Above that, the corona extends millions of miles, with temperatures far higher than the surface. Each layer modifies the light that escapes. The absorption lines studied by Payne are fingerprints of these interactions. Payne's discovery allowed astronomers to think in terms of universal principles. If all stars are mainly hydrogen and helium, then differences among them arise from mass, age, and environment rather than fundamental composition. This simplifies the study of their life cycles. It also hints at the unity of the cosmos. The same element that makes up the bulk of a distant star is the most abundant element in our body's water and in the gas swirling in distant nebulae. The revelation of simplicity leads naturally to the question of how stars remain stable. If a massive ball of hot gas is composed mainly of hydrogen, what keeps it from collapsing under its own weight? That question was answered by Arthur Eddington a year after Payne's publication. He proposed that stars are in a state of hydrostatic equilibrium, with gravity pulling inward and pressure from heat pushing outward. This delicate balance prevents collapse and provides a framework for understanding star longevity. The next part of our exploration considers how stars maintain their shape and resist collapse while they shine steadily over billions of years. Arthur Eddington, an English astrophysicist, was intrigued by the stability of stars. In 1926, he published a book in which he explained why stars do not collapse under their own gravity despite their immense mass. The answer lies in hydrostatic equilibrium. In the core of a star, nuclear reactions release energy, heating the gas. This heat creates pressure that pushes outward. At the same time, the star's mass exerts a gravitational pull inward. When these forces balance exactly, the star maintains its shape. If the pressure were to decrease, gravity would compress the core, raising the temperature and increasing the reaction rate, thereby restoring balance. If the pressure were to increase, the star would expand slightly, cooling the core and slowing reactions until equilibrium returned. This feedback mechanism keeps stars stable over long periods. The idea of equilibrium is comforting. It suggests that even in the heart of a massive star, opposing forces can reach a perfect stalemate. The tension between gravity and pressure does not result in violent oscillation, but in a steady brightness that continues for billions of years. This constancy underlies the regularity of our day and the reliability of our seasons. The sun has been shining with roughly the same luminosity for most of the time life has existed on Earth, thanks to hydrostatic equilibrium. The concept can be felt through an analogy. Consider floating in a pool of water. When you relax, buoyancy supports you. You can feel your body held in place by the upward push of water, balancing your weight. Similarly, within a star, hot gas rises and cool gas sinks, creating convection currents. The convection zone, the layer where these currents occur, transports energy from the core toward the surface. The motion is like a slow simmer, with bubbles of hot gas ascending, releasing energy, and then descending as they cool. This gentle boiling motion does not disturb the star's overall balance. Instead, it contributes to the efficient transport of heat. Understanding hydrostatic equilibrium also allows scientists to predict how stars will respond to changes. If a star exhausts its fuel in the core, the pressure decreases, and the core contracts until a new source of energy or balance is found. This leads to the next stages of stellar evolution, such as the red giant phase. Eddington's framework thus linked the internal physics of stars to their life cycles. It also connected the theory of stars to observations. By knowing a star's mass and radius, one can infer its internal temperature and pressure. The balancing act inside stars serves as a backdrop for the search for the source of their energy. Eddington himself speculated that the energy might come from converting hydrogen into helium, but the details were unknown. How could particles overcome their mutual repulsion to fuse and release vast amounts of energy? Answering this required a deeper understanding of nuclear physics. A few years later, Hans Bethe would provide the mechanisms, revealing the engine at the heart of every star, and explaining how the simplest element could power the cosmos for billions of years. In 1938, German-American physicist Hans Bethe published a series of papers that elucidated the reactions by which stars produce energy. He identified two primary processes, the proton-proton chain and the carbon-nitrogen-oxygen cycle. In the proton-proton chain, which operates in stars like the Sun, two protons collide and fuse to form a deuteron, a heavy form of hydrogen. This reaction is improbable because protons repel each other due to their positive charge. Quantum mechanics provides the key. It allows particles to tunnel through the energy barrier. When two protons get close enough, there is a small probability that they will overcome their repulsion and merge. This event releases energy in the form of gamma rays and positrons. After several steps, 4 protons combine to form a helium nucleus, releasing even more energy. The concept of tunneling is subtle. It does not involve forceful pushing through a barrier. Rather, it describes the probability that particles can be found on the other side of a barrier they classically should not surmount. In the core of the Sun, conditions are extreme. Temperatures reach millions of degrees, and densities are immense. Still, the average energy of particles is not high enough to overcome the electrostatic repulsion. Tunneling allows a small fraction of collisions to result in fusion. These rare events are enough to power the Sun because of the enormous number of particles present. Fusion is not an explosion, but a controlled burn. It is a steady process in which a tiny fraction of the hydrogen in the core is converted into helium each second. The energy produced maintains the temperature and pressure needed for continued fusion, creating a self-sustaining cycle. The reaction rate is very sensitive to temperature. A slight increase in temperature increases the reaction rate dramatically, which would raise the pressure and cause the core to expand and cool, thus regulating the process. This feedback ensures that the energy output remains stable over long times. In stars more massive than the Sun, the carbon-nitrogen-oxygen cycle dominates. In this cycle, carbon nuclei act as catalysts to convert protons into helium. The cycle is faster and more temperature sensitive than the proton-proton chain. At even higher temperatures, helium can fuse into heavier elements, releasing energy until iron is produced. Beyond iron, fusion no longer yields energy. These layers of fusion create an onion-like structure in massive stars, with different elements burning in shells around the core. The image of nuclear fusion as an engine helps us envision the core of a star as both fierce and orderly. At the microscopic level, protons dance and occasionally meet in a way that leads to a soft snap and a burst of energy. At the macroscopic level, this process shines steadily for billions of years. It is not explosive. It is akin to a controlled flame that does not flicker. The engine is quiet compared to our senses because the noise of nuclear reactions does not propagate through the vacuum of space. Beth's work on fusion provided the missing piece in our understanding of how stars shine. It linked the composition of stars, as determined by Cecilia Payne, to the energy that supports them, as explained by Eddington. It also set the stage for understanding how stars change over time. A star spends most of its life on the main sequence, burning hydrogen into helium in its core. Eventually, the hydrogen is exhausted and the star evolves. The main sequence represents a long, stable period in a star's life, akin to adulthood. Our next section will explore this stable phase, the main sequence, and the comfort of stability it offers. During the mid-20th century, astronomers assembled the Hertzsprung-Russell diagram using data from the Harvard classification system and refined stellar models. They plotted stars according to their absolute brightness and their color or surface temperature. The resulting diagram showed that most stars fell along a continuous band running from the upper left, occupied by hot, luminous stars, to the lower right, occupied by cool, dim stars. This band is the main sequence. Stars on the main sequence are in the prime of their lives, burning hydrogen into helium in their cores. The main sequence is a narrative of stability. A star enters this phase after contracting from a cloud of gas and igniting fusion in its core. Its position on the main sequence is determined primarily by its mass. More massive stars are hotter and more luminous. They appear on the upper left. Less massive stars are cooler and fainter. They lie on the lower right. Regardless of position, each star spends the vast majority of its existence in this state of equilibrium. For the Sun, the main sequence phase lasts about 10 billion years. It has been shining for about 4.5 billion years and will continue for roughly the same duration. The idea of stability is comforting. In a universe where change is constant, the main sequence provides an example of an extended, steady middle age. Stars like our Sun do not flicker or flare unpredictably. They shine with nearly constant brightness year after year. This consistency has allowed life on Earth to develop and thrive. A star that varied widely in output would have made the environment on its planets unstable. Within the main sequence, there are differences in internal structure. In stars similar to or smaller than the Sun, energy is transported outward by radiative diffusion in the core and by convection in the outer layers. In more massive stars, convection occurs in the core, and radiation carries energy to the surface. This affects how the star mixes its fuel and how long it remains on the main sequence. Massive stars consume their hydrogen quickly and leave the main sequence after only millions of years. Smaller stars burn slowly and can remain on the main sequence for tens or even hundreds of billions of years. The convection zone near the surface of a star like the Sun creates a rhythmic motion of hot gas rising, cooling, and sinking. If you could observe the surface closely, you would see granules, areas where hot plasma rises, releases energy, and then descends. The pattern is dynamic but orderly, like a simmering pot of soup. This slow boiling does not disturb the overall balance. It is part of the process that transports energy from the core to the surface. When a star exhausts the hydrogen in its core, it leaves the main sequence. The core contracts, heats up, and ignites a new source of fusion, usually helium. The outer layers expand, and the star becomes a giant. This transition marks the end of stability and the beginning of the aging process. Understanding the main sequence allows us to place stars at different stages of their lives and to predict their future. It also underscores the fact that the majority of stars we see are not in the throes of birth or death, but are quietly burning in a state of prolonged equilibrium. The calm endurance of main sequence stars sets the stage for the next revelation. After hydrogen is consumed, new reactions create heavier elements. This slow alchemy, called nucleosynthesis, builds the elements that make up planets and life. The next part of our story explores how stars become element factories, forging carbon, oxygen, and beyond, and how this process connects us directly to the hearts of ancient stars. In 1957, a landmark paper authored by Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle, known collectively by their initials as B2FH, was published. The paper synthesized decades of research on how elements heavier than helium are formed in stars. It showed that stars are not static reservoirs of material, but active factories, transmuting simple elements into complex ones through nuclear reactions. Hydrogen fuses into helium, helium into carbon, carbon into oxygen, and so on, building up elements within the periodic table. In the cores of massive stars, nucleosynthesis proceeds through a series of stages. After hydrogen is exhausted, helium fusion begins, producing carbon and oxygen. At higher temperatures, carbon can fuse to form neon, magnesium, and sodium. The process continues, with each stage requiring progressively higher temperatures and occurring in shells around the core. This creates an onion-like structure, an iron core surrounded by shells of silicon burning, oxygen burning, neon burning, and carbon burning, with helium and hydrogen shells further out. Each shell fuses elements more quickly than the one beneath it, and each contributes a layer to the Stara-Eurostrade S structure. This process of transmutation is slow compared to the violent end that follows. In stars like the Sun, nucleosynthesis does not proceed beyond helium burning. They are not massive enough to reach the temperatures required for heavier fusion. In more massive stars, however, nucleosynthesis continues until iron is formed. Iron has the most tightly bound nucleus, fusing elements heavier than iron consumes rather than releases energy. When the core becomes iron, no new source of energy can support it. At that point, the core collapses, leading to a supernova explosion that we will explore later. The elements produced in stars do not remain locked inside. Stellar winds, planetary nebulae, and supernovae expel material into space. This enriched gas mixes with interstellar clouds and becomes part of new star-forming regions. The calcium in our bones, the oxygen we breathe, and the carbon in our cells were forged in previous generations of stars. This connection is literal and profound. We are made of stardust. The concept of transmutation evokes images of alchemy, the ancient pursuit of turning base metals into gold. Stars, transmutation is a natural process governed by nuclear physics. It occurs over millions of years in a furnace of unimaginable heat and pressure. Layer upon layer builds up like rings in a tree, each recording a chapter in the life of the star. When we examine the spectra of older stars, we can see the fingerprints of these processes. The abundance of certain elements reveals the history of nucleosynthesis in the galaxy. Understanding that we are stardust alters our perspective. It dissolves the boundary between the human and the cosmic. Our bodies contain atoms that were born in ancient stars long before the solar system formed. These atoms traveled through space, were captured in the cloud that collapsed to form the sun and planets, and eventually became part of the biosphere. This continuity across time and space offers a sense of belonging to the universe that is both humbling and comforting. The products of nucleosynthesis do not remain in stars forever. The way a star ends its life determines how its elements are returned to space. Average stars like our sun end gently, shedding their outer layers and leaving behind a small core. More massive stars end in spectacular explosions. The next part of our journey explores the gentle end, the formation of planetary nebulae, where the release of material is graceful and slow rather than violent, and where the remaining core glows like a fading ember. When a star similar in mass to the sun exhausts its helium fuel, the core contracts and heats up while the outer layers expand. The star becomes a red giant, enormous and cool on the surface, but hot at the core. Helium fusion produces carbon and oxygen, but once the helium is depleted, the core contracts again. Without a new source of energy, it cannot support the outer layers. The outer envelope is not blown off in a blast. Instead, it drifts away over tens of thousands of years. This slow shedding creates a shell of gas around the remaining core. As the core heats up, it emits ultraviolet radiation that ionizes the ejected gas, causing it to glow. This glowing shell is a planetary nebula. The term is a misnomer. Early telescopes revealed these objects as small disks reminiscent of planets, and the name stuck. In reality, planetary nebulae have nothing to do with planets. They are the final breaths of dying stars. Seen through a telescope, they appear as delicate bubbles or rings, often with intricate shapes and subtle colors of green, blue, and red. Each one is unique, shaped by the star's rotation, magnetic fields, and the presence of any companion stars. Some look like hourglasses, others like butterflies, and still others like simple spheres. The process of expansion in a planetary nebula evokes a feeling of release. After billions of years of holding onto its material, the star lets go. The gas drifts into space, carrying with it elements that will become part of new stars and planets. The light from the nebula is not bright. It is soft, luminous in the darkness. Observing one can feel like watching a breath exhaled into the cold night, forming a cloud that slowly disperses. At the center of a planetary nebula remains a white dwarf, a dense core no larger than Earth, but containing about half the mass of the Sun. A white dwarf is composed mainly of carbon and oxygen nuclei packed closely together, supported by the quantum pressure of electrons. It no longer produces energy by fusion. It shines because it is hot. Over time, it will cool and fade, taking billions of years to become a black dwarf, a cold, dark remnant. The journey from glowing star to cold ember is so long that the universe is not old enough for any black dwarfs to exist yet. The gentle end of a star's life contrasts with the violent demise of more massive stars. It is slow, extended, and beautiful. It reminds us that not all endings are abrupt. Some are gradual releases, a letting go that illuminates the surroundings. The shell of a planetary nebula may expand for tens of thousands of years, slowly dissolving into the interstellar medium. The white dwarf at the center may be visible for 1 billion years, a tiny, persistent light. As we look at planetary nebulae, we can sense the quiet dignity of an average star's farewell. Yet, the cosmos also contains stars that are much larger. For them, the end is not gentle. When they exhaust their fuel, gravity does not let them go quietly. The core collapses quickly, and the outer layers rebound violently. The result is a supernova, an explosion that outshines entire galaxies. The next section examines this heavy collapse and the shockwave that sweeps through space, compressing gas and igniting the birth of new stars. Massive stars live fast and die young. After burning through hydrogen, helium, and progressively heavier elements in their cores, they build up an iron core. Iron cannot release energy through fusion. Fusing it consumes energy instead. With no energy production to support it, the iron core grows until it reaches a critical mass. At that point, electron pressure can no longer support the weight, and the core collapses in less than a second. Protons and electrons are squeezed together to form neutrons, and a flood of neutrinos is released. The core, now composed of neutrons, rebounds slightly, sending a shockwave outward. This shockwave travels through the infalling outer layers, reversing their motion and blasting them into space. The explosion is a supernova. For a brief time, the dying star can outshine the entire galaxy. The energy released is enormous. The shockwave sweeps up gas and dust, compressing it and triggering the formation of new stars. The heavy elements produced in the core, beyond iron, are created during the explosion itself through rapid neutron capture. These include gold, uranium, and many of the elements that enrich planets. Without supernovae, the periodic table would be impoverished. The universe would be devoid of many familiar substances. One of the most intriguing aspects of a supernova is neutrino cooling. During the collapse, an immense number of neutrinos are formed. These particles interact so weakly with matter that they pass through the Stara Eurostrade S layers and out into space with little hindrance. They carry away most of the energy of the collapse. For every photon of light we see from a supernova, there are billions of neutrinos streaming unseen through planets, stars, and empty space. They are silent messengers of the violence within. The shockwave from a supernova travels outward at thousands of miles per second. As it plows through the interstellar medium, it heats and compresses gas. When the wave encounters a cloud of gas, can squeeze it enough to cause it to collapse under its own gravity, forming new stars. In this way, the death of a massive star seeds the birth of new ones. The cycle of stellar evolution is not isolated events, but interconnected processes. The heavy collapse ensures that the materials for planets and life are scattered widely. The sensory imagination of a supernova is one of blinding light and powerful motion. Yet, if you were at a safe distance, there would be no noise. Sound requires a medium, and space is a vacuum. The explosion is silent to us. The only signals that reach us are light, neutrinos, and occasionally gravitational waves. The light rises quickly to a peak and then fades over weeks or months. The expanding shell of gas glows in colors determined by the elements within it. Observing a supernova can evoke awe and an awareness of the transience of even massive stars. After the explosion, what remains depends on the mass of the core. If the core is between about 1.4 and 3 times the mass of the Sun, it will become a neutron star, an object composed almost entirely of neutrons. If it is heavier, it will collapse further to form a black hole. In the next section, we will explore the nature of neutron stars and the phenomenon of pulsars, where the rotation of these dense remnants sends beams of radiation sweeping across space with clock-like regularity. In 1967, a graduate student at Cambridge named Jocelyn Bell was working on a new type of radio telescope designed to study scintillation of quasars. As she sifted through miles of chart paper printed by the instrument, she noticed a regular series of pulses. The signals arrived with remarkable precision, repeating every 1.3 seconds. At first, the team half-jokingly referred to the source as Little Green Man because the regularity seemed unnatural. Further observations revealed more such sources with different periods. These objects were soon understood to be neutron stars, the dense remnants of massive stars that had exploded in supernovae. A neutron star is a city-sized sphere, about 12 miles across, with a mass greater than that of the Sun. It is composed almost entirely of neutrons packed so densely that a teaspoon of neutron star material would weigh billions of tons. These stars rotate rapidly because of conservation of angular momentum. When the core of a massive star collapses, it shrinks tremendously. Just as a figure skater spins faster when pulling her arms in, the collapsing core spins faster. Many neutron stars rotate several times per second. Some rotate hundreds of times per second. The magnetic fields of neutron stars are extraordinarily strong. As the star spins, its magnetic axis may not align with its rotational axis. This misalignment causes beams of radiation to sweep out through space like the beam of a lighthouse. If the Earth lies in the path of these beams, we detect a pulse each time the beam sweeps past. These objects are called pulsars. The precision of the pulses rivals that of atomic clocks. Some pulsars are so regular that they can be used to detect tiny perturbations in spacetime caused by passing gravitational waves. The concept of periodicity returns in a new form. Earlier, we considered the comfort of predictable cycles in the motions of stars and planets. In pulsars, periodicity is extreme. A beam sweeps past our planet with such regularity that deviations can be measured in microseconds. The ticking of a pulsar is not just a curiosity. It is a natural timekeeper of astonishing accuracy. This precision arises from the fundamental physics of rotation and magnetic fields, and it persists because neutron stars are so stable. The discovery of pulsars provided insight into the state of matter under extreme conditions. The density, the magnetic fields, and the rotation rates push the limits of physics. Observations of pulsars have led to tests of general relativity, measurements of the interstellar medium, and even indirect evidence for gravitational waves. The hum of speed, though inaudible, is suggested by the rapid rotation. The idea of an object spinning dozens or hundreds of times per second while maintaining coherence evokes both wonder and respect for natural laws. Neutron stars represent one possible outcome of stellar evolution. The other, for even more massive cores, is the formation of a black hole. In the next and final part of our narrative, we turn to the ultimate collapse, a place where gravity becomes so strong that not even light can escape, where time behaves strangely, and where radiation leaks away over unimaginable spans. We end by reflecting on the vanishing act that turns matter into absence, and on the quiet ring of light that circles the abyss. When a star is so massive that its core, after a supernova, exceeds about 3 times the mass of the Sun, not even neutron degeneracy pressure can halt the collapse. Gravity wins completely. The core continues to shrink, and nothing can stop it from becoming a point of infinite density called a singularity, surrounded by a boundary known as the event horizon. Within this horizon, the escape velocity exceeds the speed of light, so not even light can escape. To an outside observer, anything that crosses the event horizon appears to freeze and fade, never quite disappearing. This phenomenon arises because of time dilation. As an object approaches the horizon, time for it slows relative to distant observers. The falling object never quite appears to reach the horizon. It just becomes fainter and redder. Black holes are defined by their mass, spin, and charge, but otherwise they are simple objects. They warp space-time so strongly that paths of light curve around them. At a certain distance, outside the event horizon, lies the photon sphere, where light can orbit the black hole. This ring of light is unstable. A slight disturbance will cause a photon to either fall into the hole or escape. The image of a black hole includes this bright ring surrounding a dark shadow, as captured by the Event Horizon Telescope. It is the ultimate quiet, light itself getting trapped in orbit, circling endlessly until perturbed. In the mid-1970s, Stephen Hawking proposed that black holes are not entirely black. using quantum field theory in curved spacetime. He showed that pairs of virtual particles can form near the event horizon. One particle falls in, and the other escapes as radiation. This process, known as Hawking radiation, implies that black holes can lose mass and eventually evaporate over extremely long timescales. For stellar mass black holes, the evaporation time is far longer than the current age of the universe. For tiny hypothetical black holes, the process would be faster. The idea that black holes can leak away undermines the notion of absolute permanence. The vanishing of a black hole is a slow whisper rather than a bang. Over billions or trillions of years, Hawking radiation would carry away energy, causing the event horizon to shrink. From a safe distance, the black hole would grow less massive, its gravitational pull weakening, until eventually it disappears. The time dilation near the horizon means that from the perspective of infalling matter, the end comes swiftly. But to an external observer, it is stretched out. This duality challenges our intuition about time and endings. The concept of a photon sphere adds to the imagery. Imagine light trapped in orbit, circling a black hole indefinitely, creating a ring of pure light around a dark center. It is a place where the usual rules seem inverted. Instead of matter following curved paths around a source of light, light itself follows curved paths around an absence of matter. This ring is not a physical object, but a path that photons can take. The ultimate quiet of this orbit speaks to the stillness at the edge of the ultimate collapse. As we reach the end of our journey through the history of human understanding of the stars, we have moved from the fireside myths of prehistory through the clay tablets of ancient civilizations, the ordered spheres of Greek philosophy, the navigational compasses of Polynesian voyagers, the meticulous records of Chinese astronomers, the telescopic revelations of the Renaissance, the laws of motion and gravity, the measurements of parallax, the decoding of spectra, the classification of stars, the discovery of their simple composition, the balance that sustains them, the fusion that powers them, the stability of their midlife, the factories that create heavy elements, the gentle release of planetary nebulae, the violent rebirth of supernovae, the precise ticking of pulsars, and finally, to the enigmatic quiet of black holes. Each step has layered human curiosity with increasing knowledge, weaving a narrative that connects our existence to the cosmos. The stars have guided, inspired, and humbled us. In contemplating their birth, life, and death, we glimpse a universe that is vast